Alright, so we want to look at a confidence interval exercise. This is actually out of your homework in Wiley Plus. And here's a good example of an applied situation here. So it says a city planner who wants to estimate the average monthly residential water usage in a city. Okay, he selected a random sample of 37 households and found that sample mean water usage to be 3,405.40 gallons, that is. Okay, based on earlier data, the population standard deviation of the monthly residential water usage in this city is 387.30 gallons. Now it's very important to notice what that just said right there. It said, based on earlier data, the population standard deviation. So here we know the population standard deviation. That's very important because there's one method to go about constructing a confidence interval when you know the population standard deviation. There's other methods to go about constructing the confidence interval when you don't know the population standard deviation. So that's very important to recognize what that last sentence just said right there. Okay. Now it says make a 97% confidence interval for the average monthly residential usage for all households in the city. Okay, so what we are going to do is, well, first let's label what we know, I suppose. The first sentence gives us the second sentence rather, gives us two important pieces of information. Let's see here, let me get started. We have, oh, that's not the right one. Here we go. We have n equals what? Okay, 37. Okay. We also have the sample mean is x bar, and that equals 3,405.40. Okay. Then the important thing we talked about earlier, that is sigma. That's a population standard deviation. That is 387.30. Okay. Those are the three pertinent pieces of information we really need. And of course, the whole point of this exercise is that we need to construct a 97% confidence interval. Okay. Alright, now I suppose before we even get started, let's talk about estimators. Okay. Now remember, with this chapter we are trying to use sample statistics. Remember, a sample statistic is a numerical measure that describes a sample. So that is things like x bar, or for like S is a sample standard deviation. So here we're going to use x bar to estimate a population parameter. So we're going to use x bar to estimate mu. So x bar is what's called an that's not right. We can do this. An estimator for mu. Okay. So we're going to do this. X bar equals mu. Now we know, it's not going to be exactly mu, but it's an estimate. Okay. Now let's go over here to the confidence interval. Okay. Now before we can construct our interval, we need to know the z value that's associated with a 97% confidence interval. Now there's a chart in your book. There's 4 or 5 common confidence intervals, and you can certainly memorize the z values associated with those confidence intervals. Or if you can't remember them, it's really no big deal. You can just always construct them on the fly, like I'm about to do right here, because to be honest with you, I've forgotten which z-value is associated with a confidence interval of 97%. But here's how you go about doing that. So what we want to do is construct a 97% confidence interval around mu, our estimate really. So x bar equals mu. Now, if this shaded part right here, if all of that is 0.97, that is 97%. Okay, let's see here. Then what goes there? And what goes there? Now remember, this is a symmetric distribution. So if 97% of the data is right there in that shaded portion, what portion is left between both tails? Well, 0.97, well, 1 minus 0.97 is 0.03. Now 0.03, that's the amount in both tails. But both tails have to contain the same amount of area under the curve. So if you divide by 2, what do you get? 0.015 in both of those tails. 0.015 there, and 0.015 there. Okay, so now the question is, what is that z-value, and what is that z-value? Well, we did this in chapter 6. Okay, this was when we reversed the process of when we were first given a z-value and finding a probability. Here we're given a probability to the left of z when z is unknown. So here the area to the left of z is 0.015. Over here the area to the left of z is what? Well, it's actually 1 minus 0.015. Okay, so to look those values up in your z-chart using the appendix in the back of your book, or you can use your calculator and find the inverse norm of, to find the left-hand z-value, you can find the inverse norm of 0.015, or to find the right-hand z-value, you can find the inverse norm of 1 minus 0.015. You'll see for the left-hand z-value, you get, let me see if I can squeeze it in here, negative 2.17, and for the right hand you get positive 2.17. So the z-value we are looking for is z equals 2.17. Now, you could use negative 2.17 if you want to. It won't affect the answer either way whenever it's all said and done, but convention is we always pick the positive z-value. And you'll see why that is in just a few minutes, as far as it not mattering between the negative and the positive, but we always pick the positive one, just for being consistent. Okay, now, we actually have all the information we need now to solve this. Okay, so let's review how to find the confidence interval. Let me put a different color on. The confidence interval is given by x bar plus or minus z times sigma. Oh, sigma, oh, I said that a little bit wrong. Sigma sub x bar, the standard error. Okay, not just times sigma. Good thing I called that error. It's the standard error. Remember, and if you don't remember what the standard error is, that is z sub x bar. Well, let's see, not z sub x bar, sigma sub x bar. That is sigma over the square root of n. Okay? So we need to use this right here to construct our confidence interval around our estimate for mu. Okay, so let's go down here and let's see about our answer. So we can say x bar, oh, forget about that. What is x bar? That is 3,405.4 plus or minus z, we found b was 2.17. And now what is the standard error? Well, we know sigma is 387.30 and we know n is 37. So we can say 387.30 divided by the square root of 37. Okay. Now that is our confidence interval. Now we just need to simplify that. Now remember, just like say with the quadratic formula, you know, there's two answers embedded inside the quadratic formula. Same thing going on here. Well, there's two answers right here. One of the answers is the lower end point, and the other answer is the upper end point. So the lower end point is 3,405.4 minus that right-hand side. The upper end point is 3,405.4 plus that right-hand side. So let's see what those actually equal. I'm actually going to take a sec and type this in my calculator. Let's see, 3,405.4 plus 2.17 times 387.3 divided by the square root of 37. Make sure to use your calculator correctly and take into account order of operations, putting your parentheses in the right spots and everything. And it looks like I am getting, okay, for the upper end point, that's 3,543. Let's see, how should we round? 2 decimal places is the direction, say. So that's going to be 0.57. Now the other answer is the lower end point, and that is going to be 3,405.4 minus 2.17 times 387.3 divided by the square root of 37. Again, be careful with your order of operations. And for that lower end point, I am getting 3,267.23 if we round to the nearest second decimal place. Okay? So my interval is, my 97% confidence interval is 3,267.23 to 3,543.57. There's my confidence interval. Okay? So we are, let's just draw a conclusion here, 97% confident that the true population standard, not standard deviation, the true population mean is in that interval. Okay? Another way to think about this is, or maybe more technical way to think about this is, if you take every possible sample of size 37, okay, and you calculate the mean. So there may be just an inordinate amount of possible samples here. But if you, depending on the population size, of course, but if you took every possible sample of size 37, calculated the mean, 97% of the time the mean would be inside this interval. That is, 3% of the time we would expect the mean not to be in that interval. But we're 97% sure it is in that interval. Now, so that's, there's our solution. We are done with what the directions asked us to do. There's our interval, our confidence interval at 97%. Now, I'll answer my own question. What if we said that that is too wide of an interval? That is, we say that's a bad estimate. We want a closer estimate for mu. Now, this isn't, I'm not talking about confidence level. I'm not talking about increasing the confidence level. I'm talking about getting a smaller interval around mu. One way to do that is to increase the sample size. That is, if we increase the sample size, you get a better estimate, a tighter estimate around mu. So there is our current interval. That's at 97%, and our sample size is 37. Okay. What if we, let's see here, let me go to a new color, maybe, let's see. Let's just use grayish for this, since this is not even part of what Wiley asked us to do. Let's say we want a better estimate. That is, we want a smaller interval around mu. Now, what I said earlier is the way to do that is to increase sample size. Now, I'll show you why that works. Let's say n equals 100. So instead of 37, n equals 100. Again, this is a different question. This is just something I just made up. Okay? Well, guess what? We're leaving everything else the same. So sigma is going to be the same. That's still a 97% confidence interval. The only thing that has changed is the sample size. So the confidence interval for this would be x bar, which again is the exact same, 3,405.40 plus or minus, let's see, it is z, which is 2.17 times sigma, which is 387.3, but this time n is 100, so divided by the square root of 100. Now let's see how that changes our interval. Okay, so just like before, there's two answers embedded here. Now let me use my calculator to just do the arithmetic. So we have 3,405.4 plus 2.17 times 387.3 divided by the square root of 100, which is 10. Okay, so I got 3,489.44. Okay, that's for the upper endpoint of my confidence interval. Now let's find the lower. That's 3,405.4 minus 2.17 times 387.3 divided by the square root of 100, which again is 10. Okay, and so I found that the lower endpoint here is 3,321.32 So my interval here is 3,321.36 to 3,489.44. Okay? I shrunk my interval, you see, here comparing this right here and this right here. All we did was increase the sample size, but you see how my lower endpoint is actually higher and my upper endpoint is actually lower. We decreased the width of the interval, which means we got a better, more accurate estimate for our population mean mu by simply increasing the sample size. Another way to think about that is we decreased our margin of error. Now, we actually didn't compute the margin of error before, so let me switch back to red and go back here. The margin of error is just this portion of our expression. Oop, I go through 37. That's E. So E here equals, let me calculate it, 2.17 times 387.3 divided by the square root of 37. E here, the margin of error is 138. If we round the 2 decimal places, 17. That's the margin of error. Now, if I go down here and compute the margin of error, again, E is this part right here, the factor that you're adding and subtracting each from the mean to create your confidence interval. So here, the margin of error is, well, let's see, 2.17 times 387.3 divided by the square root of 100, and the margin of error is 84.04. So you see here how the margin of error right here was decreased from 138.17 to 84.4 by simply increasing the sample size from 37 to 100. So we made a more accurate estimation for our population mean without decreasing our confidence. Okay. We actually didn't do anything different. We kept the same sigma, kept the same x bar. All we did was make n bigger, and we got a better estimate for the population mean. That is, we decreased the width of our confidence interval. Again, all that I just did right there had nothing, well, was related to the exercise, but wasn't part of the actual exercise in Wiley Plus. This was just a little bit of extra exercise, extra bit of help for study for free. Now, not to say this doesn't pop up in other questions, but right here, that wasn't part of the exercise. So, if you have any questions, feel free to email me or stop by my office. This is the first portion of chapter 8. I'll do a few more tutorials regarding the other scenarios for confidence intervals. Again, this is a confidence interval where we knew sigma, the population standard deviation. If you know a sample standard deviation, you'll have to do a different method. And we will go over that, if we haven't already, using the T-chart. Okay, but this was an example where we knew, well, I'll scroll back up here, where we knew based on earlier data, the population standard deviation was known, which was this guy right here. Very important. If you know the population standard deviation, this is the process you'll follow pretty much every time. Alright, you guys have a good weekend. I'll see you next week.